Before we begin, someone on Piazza asked me just to quickly explain what the change address was. So if we go ahead to, from the homework, if we go ahead to like search Alex's public key on here, we'll go ahead and see that there's two transactions here. One of them is like this address is getting money, and the other one is it's the money is being withdrawn from it. So because like it was me sending Alex money, it's this transaction that we're interested in. And see, there's two inputs, right? And like I told you, like I was paying her 0.032 Bitcoin. So that's why this one is the one that actually got sent to her, while this is my change address. The top one is my change address, because whatever's not being sent to her I'm sending it back to myself. So that's why that one was the change address. Yeah.
So when you send Bitcoin, you end up sending everything out and send yourself back, but you didn't send it.
You end up sending out one full transaction output. So let's say Philip sent me one entire Bitcoin at some previous time, and that's like, let's say Philip sent me one entire Bitcoin and Max sent me like 2 Bitcoins, and I only want to send like 0.5. I'll just take whatever's closest, so I'll take like Philip's because it's only 1 Bitcoin, and then send 0.5 to Alex, and then 0.5 back to myself. So I don't have to spend like 0.5 to Alex and 2.5 back to me. As long as I spend one transaction output. Yeah. Okay. So yeah. On to the lecture. Before we begin, I'm going to give a little demo of how private and public keys work. So this is a online. It's a piece of software called Bitcore. It's just Bitcoin libraries that make a lot of things really easy for development. It's written in Node, so it's really easy to like implement into other things. But I'm just going to be using it in a terminal to show some cool stuff. So as Max talked about last week, private keys are essentially you can just a random number and any like 2 to the 256 bit random number. So we're going to go ahead and just like create a private key right here. And so what I'm going to do is I'm going to take this function right here, which all it does is says to create a 32-byte random number, random buffer, 32 bytes, 256 bits. And then I'm going to go ahead and turn that into, right now it's a buffer, but let's go ahead and turn that into a number. Oh, whoa. And number. Yeah. So that's, all right, there we go. We now created a random number, right? What we can do is, right now it's in hex, but we can go ahead and turn that to a number. There's our 2 to the 256 bit random number. And all we have to do is, if we want to create this is essentially our private key that we've created here. Well, actually that's not the private key. This is going to be the private key. There's our private key. We just created a private key. And notice how like nothing I did actually depended on the internet. I didn't have to check with anyone like, oh, is this random number already taken? Everything was just done locally on my computer. And then if I just want to turn this into a public key, I can just pass it through another function. That I pass my my private key as a function that gets turned into a public key. And there we go. We have my public key address that we just created from scratch. So how does this differ from? So now let's compare this to something like Gmail. When I created a Bitcoin private key and public key, essentially what I did was I chose a random number, and I started off with my private key, and from that I generated the public key. While on Gmail, what you do is you choose your username and password kind of independently. Your password doesn't depend on your username. Your username doesn't depend on your password. And what you do is to check to make sure no one's already taken your username. You have to like check with some central repository, which in this case is Google, whichever main Google mail server you use, to make sure that that email address isn't taken. But as Max explained last week, the space of possible private keys is just so large that it's okay to just randomly generate one because it is so like negligibly likely that you'll choose the same random number as the one that's already been taken.
But what if it does happen?
What if it does happen? It's like, yes, technically then both of you can spend money in an account. But what often will happen, which I'll go into later, people don't use the same account more than once, which I'll explain why. But because of that, most likely, unless you like somehow get the same private key as one that was created pretty recently, if you like get one that was used like from like 2 years ago, chances are that there's probably not going to be any money in that anyways.
If Bitcoin is so secure, why doesn't everything else just run on the same?
Like why did I mean a lot of things do like use the same idea of, and also, well, I don't know what's like the best way to explain.
I mean, it's just public private key cryptography.
Yeah, like a lot of things do run on this software.
Or unique to Bitcoin.
But is Bitcoin like more secure?
Not necessarily more or less. It just is mathematically secure.
It's like instead of like here you're just putting all your trust in like math and making and like and probability, while I mean Gmail is also pretty secure because you're putting all your trust in Google, but saying that like, oh, because of them they're not going to like give out the same email address to multiple people, and they're not going to let anyone try to like access your email, which I'll actually get into a little bit about why like Google, because of that you can do stuff like rate limiting, which I'll get into in a little bit. Yeah.
I kind of lost track. So what are these keys for again? The public private keys?
The private key, so the public key is your it think of it like almost like your address.
So it's constant.
Yes. Once you create a private key, you create a public key, and these two are linked together. Like,
Okay.
yeah.
So the public key is your address. So in case I want to send you money, I would use your public address, your public key.
Yes.
And what is the private key for?
The private key is for signing transactions. So think of it almost as like a username password model. Like I tell everyone my email address, and anyone can send me emails, right? But only I can send emails from my account because I have my password. So same with the private key. Whoever has the private key can send money from an account.
From that public address.
Yes.
And a private key is constant too.
Yes.
So it's essentially a more complicated password, right?
Yes.
Oh, it's
Yeah.
It's a different.
You're shit out of luck.
Okay.
Make sure you repeat questions.
Oh yeah. Yeah. All right. So basically, what I described is to get your private key. You basically, essentially, my point was to show that like your private key is generated from your public key. And so one thing we're going to look at right here is on the structure of these addresses. So why don't we just use these like really long numbers? Mostly just because they're really long and like no one wants to type out that many characters. So instead of using a base 10 like decimal system or even like hexadecimal, we use something called base 58 where we have like 26 letters, 26 lowercase letters, and 10 Roman numerals. But as you notice, that's 62, not 58. And the reason that is this is completely coincidental. I didn't mean for this to happen, but when I generated the random URL for today's like attendance, it had 2 O's in it, and people kept asking me like, are those O's or zeros? So these were O's. But so in order to avoid this problem, because what we do is we just like often you'll put your public key on like some website that people can like read off or something. So just to avoid this kind of confusion, we just go ahead and get rid of the uppercase O, the uppercase I, the lowercase L, and the 0. And so that's why we get base 58. Just a little quirk. And so now we can go into something Bitcoin wallets a little bit. And so what do wallets actually do, right? At the most fundamental level, all they do is hold your private key and give you the software to be able to sign transactions, right? So the signing of transactions is something that we'll be going into in a little bit later this lecture and more in later lectures. But I'm going to talk more about the actual storing of private keys. So wallets take 2 main forms. They're called hot storage and cold storage. Hot storage is basically anything that's connected to something digital, like something that, like whether it's on your computer or in the cloud or something that's something digital, while cold storage is encoded in the physical world. So examples of hot storage are you have online web wallets like Coinbase, where basically your private keys are stored in the cloud. That's why you can access them from any computer essentially. You can log on to your Coinbase website, onto the Coinbase website and log into your account and send money from anywhere. Then you have the like smartphone and desktop apps, where basically the private keys are stored on the hard drive of the device, which is good because they're not in the cloud. It's much harder for someone to hack that because it's at least not out in the air. But if anyone gets a virus onto your computer or anything like that, they can still access all the keys. Yeah.
Oh, wait, could you just like differentiate between hot storage and cold storage?
Yeah. Hot storage is any wallet that stores your private keys on some sort of digital medium, while cold storage is it stores it in something physical or really just non-digital.
It's not network connected.
Yeah. Yeah, actually, that's a better way to say it. It's not connected to the network because your laptop is probably going to be connected to the network pretty often. So it's still there's a link that someone could potentially like hack into your computer and get the information.
So those are examples of cold storage.
The smartphone apps and online web wallets are examples of hot storage,
Okay.
and then these three are examples of cold storage.
But aren't they online stuff too?
Which one? Oh no. So I'll go ahead and show so how paper wallets work is essentially instead of storing your private key on your computer, like this, all it is it's just a number, right? So in fact, we could store this on a piece of paper, just write it down somewhere, and hide it away in your closet or something, and no one can really access it. One cool like website that's often used for making private keys is this one called Bit Address. And so if you remember, what you have to do to create a private key is just create a random number. And so computers are pretty like pseudo-random. They're not as random as we'd like them to be. So this one actually kind of uses I'm just doing random mouse movements, and it's using that to generate a random number, which gets turned into my private key. But essentially what I can do here is, what they actually suggest you to do with this website is actually download the HTML and like turn off your Wi-Fi and everything so it's not connected to the internet when you make this. You create this, you print it out, and then close this web page. And this key doesn't exist anywhere other than the physical piece of paper you have it on.
So your wallet is just wherever you store your password?
Essentially, yeah. Now, the thing with this is if you want to actually make money with, like actually make transactions with it, you do obviously have to put it back into some software client in order to like actually send money back and forth. But this is more for like the storage purposes. If I want to store Bitcoin, if I'm not like planning on making any transactions with it at the moment, just for safeguarding, I would like to keep it off of a computer. If that makes sense.
You just have to type everything back in.
Yeah, you just have to, and it's really not. It's really not that long. It's like, this is my private key. It's not that many characters. You can even scan it with your QR code. What you also can do is cover up you can publish the left side of this paper, and that's like your public key, and anyone can you can put it on the wall and you can scan it and send you money and whatever.
Quick question.
Yes.
Could you go back to so the left hand side one is the public one, and the right hand side one is the private.
Yes.
And let's just say that I put, okay, fine. So you said that I can put the barcode on the left hand side for people to give me money. What's the right hand side barcode for?
The right hand side is your private key.
So I can make transactions with that.
Yes.
Okay.
So that's why you want to keep that in a safe location. So when you actually decide to be able to transact money, you're gonna have to use some sort of wallet, like on hot storage wallet, but you can't actually send money from cold storage. Yeah, because to transact on the network, you have to be connected to the internet.
I just have a simple question.
Mhm.
It might sound kind of dumb, but let's just say that I brute force through several barcodes, right? And keep scanning through them. And I'm bound to run into one barcode which will conform with someone else's barcode. And I can make a payment to my account through that, right?
Yes, but brute forcing these is, like Max said, even like some of the best computers, like the whole like grain of sand for every Earth on a piece of grain of sand. Like there's just so many you won't be able to brute force it. I'll get into a little bit about when brute forcing does actually work, though. All right, next one is hardware wallets. Hardware wallets are basically they're like external devices, specifically designed for the purpose of being cold storage. They do all their they store your private keys on an area of the storage memory called a trusted execution environment. And what these actually do is basically you plug it into your computer, and your computer, you'll have a client on here that will create a transaction, but it can't sign it because it doesn't have the private keys. So what it does is you plug this hardware wallet into your computer with a USB. It sends the unsigned transaction to your hardware wallet. The hardware wallet will sign the transaction and then send the signed transaction back to your computer. So the benefit of this is that your private keys never actually leave the hardware device. The hardware device is the one that does all the signing, and so your laptop never knows. And so if anyone's has a screen tracker or something snooping on your laptop, they don't actually ever get access to the private keys.
So you can never hack this hardware wallet even when it's connected to the computer?
It's very hard. It's much harder than hacking a computer, at least. And most of these guys, like Ledger, Trezor, Case, these guys have been around for a few years now, and they put a lot more effort into their security of their device than your laptop probably does. Yep. And finally, the last one, which I just find as a really cool concept, is called brain wallets. So the benefit of a brain wallet is, if you think about it, this isn't actually that bad. It's just a number. If you just memorize that number, you don't actually even have to keep it on a piece of paper. If it's on a piece of paper, someone could still go snooping in your closet, find the piece of paper or wherever you store it. If you just memorize it, there's nothing to hack, nothing to find. There's really no way anyone can get the private key out of you, unless short of torture, basically, right? So basically, but the problem is it's very hard to memorize such a long set of numbers. So what we instead do is you memorize a set of words that you can then hash into a private key. So I can give an example of this right now. So we can go ahead and take a set of random words. Correct horse, battery, staple, Max Fang. And we'll just go ahead, take that, and turn that into a SHA-256 hash, right? Or into a buffer. And now what we can do is pass this buffer into a SHA-256 hash. And we get out a brand new buffer. And then we can go through the same process I went through at the beginning of class to basically turn that into a private key and public key. And so the good thing is now all I have to remember is these 6 words. Typically, what it's traditionally done is 12 words, not 6, just to add a little bit more entropy into the program. But the big issue with this process is that humans are not as random as we like to think we are. And yes, the namespace of words and is pretty high, but when we actually end up choosing words, we do it pretty not very cleverly. And so there have been examples of, so if you just here's where brute forcing can come in. If people who are using brain wallets try to you can start brute forcing those. So now you just have to check dictionary attacks, right? And there's someone who used a line from some obscure 18th century poem that no one's ever heard of, but this was a big story a few years ago. But all his money and funds got depleted just because you can easily dictionary attack these things because there's no way to rate limit a brute force attack. So the thing with Gmail, right, is after a certain number of attempts, 10 attempts, they're gonna block your IP address, right? But what we do here is there's no one blocking it. All you're doing is generating random numbers. So you already know the public key associated to an account. So you just, on your computer, you just have to keep trying random private keys and turning those into public keys, see if they match. If not, you just keep doing that again and again. And since there's no rate limiting, it's actually pretty easy to brute force these brain wallets. Yeah.
So what are the consequences of getting it and the private key being lost forever? So I can't.
The money will be sitting on this account, and it can never be withdrawn.
No way.
It's no way. You'll hear if you lose your private key, the money is gone. You'll hear stories about I don't know how often this is true or people are just saying it, but you'll hear people say like, oh, I like mined Bitcoin back like in 2009 and I had like 10,000 Bitcoins, but my hard drive crashed and I don't have the private keys anymore. So, yeah.
So do you get some sort of like receipt saying when you opened your Bitcoin or not?
So can you explain what you mean by that?
So I mean, like if somebody keeps trying to open up your Bitcoin by
Yeah.
like putting in like,
Mhm.
constantly putting in private keys,
Yeah.
and they eventually open it, you get some sort of notification saying it's been opened.
Well, you'll see that the funds are transferred out.
Yeah.
I know that. I mean, like,
No.
That's
You
it.
don't know?
No.
Okay.
You won't know when someone actually opens it. You'll just see the money's gone, and you're not gonna be able to know who took it. But so like brain wallets aren't necessarily bad. Like as long as you will probably want to use like a random word generator to create your list of 12 words, not like try to come up with them on your own or try to like take a line from a poem.
Can you delete the private key? I disabled it.
Disable.
Private key.
Um,
You forgot it, but you don't want people, if anyone find the key to spend money. So
If you forgot it, I don't think I don't think like why does it matter to you, right? If you can't withdraw their account like from the account.
In your Coinbase.
Oh, in your Coinbase. So Coinbase is a little bit different. I'll get into that in a minute.
What is the tech with a brain wallet? Did they know what the brain wallet is? I mean, otherwise there are a lot of addresses to it. I mean, how did they know what to target this one? That is part of everyone, right? I mean,
How can you know if something's a brain wallet?
I mean, this particular case you said where they hacked them. I mean, how did they know? Because I guess there are a lot of addresses. So
This actually method of using words to generate private keys is actually not only in brain wallets. A lot of wallets actually do that now. So if you, especially on like not web wallets, like if you use something like Mycelium, which is like a wallet that's purely on your phone, when you actually create a wallet, it'll tell you like, hey, these are the 12 words that you should probably write down somewhere, and that way, if this phone crashes or something, you can pull it up, you can get a new phone and like input those 12 words. So in fact, actually most wallets end up using a word method.
So that hackers knew sort of that it's gonna be.
Yeah. This was all part of like, yeah.
What is a command that makes you transfer the word into a string?
That's a hash function called SHA-256, which Philip will be talking about in a few minutes. Okay. Yeah. So one way we can make brute forcing actually a little bit harder is something called key stretching, where basically what you normally do is, right, you take these set of 12 words and you pass it through a SHA-256 hash and get a private key and get your private key, right? But one thing we can actually do is, what if we just take this whatever came out of this hash and just pass it through the hash again and again, and you just keep doing this a lot of times. Let's say you do this, like, for example, 2 to the 20 times, right? For you to regenerate your private key, yes, that's a lot of work. You have to do the same hash like 2 to the 20 times. But at least it's only like a constant. It's like you have to do one time, you have to do 2 to the 20. If someone's trying to brute force you, every attempt they do, they have to do it 2 to the 20 times. And also then they also have to know how many times you passed it through the hash. So it makes brute forcing a lot harder. So I'm actually not sure if most wallets do key stretching or not, but this is one way to make it actually a little bit more secure.
So what is my final private key? Is it the one that I pass in initially, or is it the one which I get after 2 to the power 20 times of passing through that shot?
So like I said, the private key can be anything you want, right? So I could, at any point, I could stop and say I want to use this as my private key. But in key stretching, what you're going to do is your last one is going to be your private key. So that way, if someone wants to like start off with a set of words and like try a bunch of random words, every time they try a bunch of words, they have to do 2 to the 20 hashes in order to do one attempt.
Oh, so you're saying like the first 12 words I use, I hash them to 2 to the power 20 times and I get this?
Yes.
I always get this number?
Yes. The hash will always, like, if you start with the same 12 words and pass it the hash, it'll be the same every single time, which, once again, Philip will talk about. He'll go more into the cryptography of this stuff.
I'm confused about how, like, since the wallets are limited by, like, the human brain, why do they start with those 12 words to begin with? Like, because the wallet isn't limited by starting with 12 words, and it could be just a random string and then.
Oh yeah. So her question was, why do we only use 12 words instead of just any random string? Yeah, you could use any random string. It's just become like normal protocol at this point to use 12 random words because 12 random words gives about a roughly equal namespace as 2 to the 256 if you use like a full dictionary set of words.
I guess I'm just confused. Like, it seems like it's reducing the security of this. Like, if you're gonna go with key stretching,
Yeah.
then why not just start by like not having something that?
Because the idea is you want to start off with something that you can memorize.
But if you have a wallet, then why does it matter? Right?
Oh, because yeah, that's true. You could write it down somewhere. It just for simplicity's sake, like if you want to still be able to write down a bunch of random words instead of like a 20 character long like string
I
of.
see. Okay.
Lauren, you had a question? Oh, okay. Like my awesome animations. Okay, choosing a wallet, right? Two things you should consider is features and security. I'll talk about a few of the important ones in each of these. Features is you have something called multi-signature addresses. So one of like the coolest things that like one of the most important steps that Bitcoin made was it allowed a wallet to be owned by multiple people. Basically, and what you can do is you can set up schemes where you can basically have multiple people own an account, but you only need a certain number of people to sign off on a transaction. It's called like M of N. So right, so you could set up like, for example, let's say we had a large amount of funds for this decal, right? And me, Max, and Philip each have private keys. What we could say is we need 2 of 3 people to approve a transaction in order for it to be made. So we'll create a 2 of 3 multi-signature account. Or you could do 2 of 2, where it's just me and Philip. Or you could do 1 of 2, where like that essentially acts as a joint checking account, where we have the same account, but only either of us can just spend the money unilaterally. And then you can also use multi-signature for some security benefits, like I'll go into a little bit. Yes.
What would happen if one of the parties would lose one of their keys?
One of the parties lose one of their keys.
Yeah.
Then so if you have a 5 of 5, then if one of them loses it, money's all gone.
Yes, okay.
But if you have like a 3 of 5, for example, right? If one of them loses it, what you want to do is immediately get 3 of the people together, move all the money to a new account, and create a new 3 or 5 scheme. Yeah.
I'm so sorry. Go on.
Sorry. Yeah.
Okay. Can you be logged in several platforms at once?
Like use multiple wallets.
Yes.
So everyone loses their money. If one person.
If you have a 5 of 5 account and if one person loses their key, then yes, everyone loses all their money.
Right, so presumably it could be like you could have 5 of these accounts and you should control all of it. And just be more secure.
But like, so what's the? Yeah. So actually, yeah. There are reasons why you will create a private, multi-signature account with yourself. Which, for example, one of the wallets that I use is called Copay, and so if we go to the settings of this wallet, advanced wallet information, right? We see this is actually a 2 of 3 account. What I've actually done here is I have 1 key on my laptop, 1 key on my phone, and I gave 1 key to a friend. But basically, I need 2 of 3. So what I want to do is have like let's for this example, let's assume it was actually 2 of 2. It'll act as like 2-factor authentication, right? So I have to approve something on my laptop and on my phone. And now the reason I gave 1 to my friend is that let's say my laptop gets stolen or my phone gets broken, I can then go to my friend and say, hey, I need your help to like move all my funds to a different account. But the thing is, since it's 2 of 3 and he only owns 1 of the keys, he can't just take all my money either. Yeah.
He could blackmail you though.
He could blackmail me if I broke one of my devices. Then I guess at that point he has like power saying like if he doesn't want to help me, I'm kind of screwed. Yeah.
What if both? I mean, what if you lose your phone and laptop on the same day?
Then I'm also screwed. So then what you could also do is do 2 of 4 and give it to two different friends and hope they don't collude. Yeah.
Wait, so you can't immediately physically decide that I want to give these to like my two friends after you lose them? You have to do that beforehand.
Yes. When you create the wallet.
Since this is enforced by miners who verify, does this increase the size of your transactions?
Yes. So I'll actually get into that in a second. So yeah.
What's the limit on how many keys you could have on a single account?
I actually don't know. Is there a limit?
There is a limit.
I'm not sure, but I don't think there is. I don't think there is one, but keep in mind the larger it is, the more fees you're gonna have to pay for the transaction. So the reason for that is often the way to normally do like this kind of secret sharing is like through threshold cryptography. Like if anyone's taken CS70, where you do like the whole secret sharing schemes and everything. But the problem with that is once this scheme is used once, it's no longer reusable. Once the people put together their private keys, that private key has been like created public to all the people in this system, and now it's not reusable. And also you have to like trust one central person to put together the private keys and not run away with the money at that point, right? So what Bitcoin actually did was, instead of using like cryptography to achieve multi-signature, they just included it in the protocol, where in the verification stage, if each transaction can be marked as multi-signature, and so it'll just check to make sure it has the different private keys it needs. So it's been completely implemented through code rather than cryptography. Yeah, that's what I was saying. Another cool feature that a lot of people use, important feature is what you actually want to do is generate a new private key for every transaction you make. So I know up till now we've been kind of assuming that your private key is your identity, but one of the whole reasons a lot of people use Bitcoin is because they want to be really anonymous. And so basically, if you only use one private key or account for all your transactions, because everything is available online, you can just go on blockchain.info. Anyone can see that, like, hey, you own how much Bitcoin you actually own. And that's something people don't really want to make public. So what you'll actually do is you'll create a new private key for every single transaction you make. So you'll actually be the owner of like thousands of Bitcoin accounts. And then your wallet software will actually be the one that does all the heavy legwork of like combining accounts in order to make larger transactions. Yeah.
I thought that the private key was hidden and it's the public key that other people can see. And
Right.
you can own as many public keys as you want for multiple addresses to kind of distribute.
So each private key can only generate one public key.
Oh, so they're linked.
Yeah, the private and public keys are like they're a pair. And so if you want to create multiple public keys, what you also have to do is create multiple private keys and then use those to all hash to a new public key. And so this is very common practice. This has been being done in Bitcoin almost throughout. Another side benefit of using a new private key every time is what you can do is, let's say you want to buy something online. They'll tell you, hey, send money to this address, and it will be a brand new generated address. So now all they have to do is actually just check to see is money sent to this account, because you're the only one who really knows about this address because they just generated it for you. So that way they don't have to bother checking like, oh, which account sent money to this address. They just have to know someone did. But this got very cumbersome because what happened was every time you create a new private key, you do want to back up your wallet constantly, right? Because you don't want it so your hard drive crashes and suddenly all your information is gone. So what you actually do is you back up your keys. The thing is, if you're creating a new key every transaction, what you're going to end up having to do is create a new backup every single time you create a transaction. Otherwise, you'll lose all the money that was linked to that specific private key. So there was this something called BIP32. It was called BIP32 because if you remember from our first lecture, Bitcoin improvement protocols are improvements to the new updates to the Bitcoin software. And on BIP32, they added something called hierarchical deterministic wallets. And what this basically allows you to do is take any private key and create a child private key out of this that you can determine this child private key from your parent private key. So often in a very simplified way, all you'll do is like, if my private key was like 55, and this hash to like some random number like 32, for my next private key, what I'll just do is I'll do like 56 and get that to hash to like some other random number, right? And basically what you can do is, as long as you always remember this private key, you can quickly generate these other ones because it's pretty simple to just increment one and just what your other private keys are. This is obviously a very simplified method of doing it, but the general idea is you can quickly figure these out from this original private key. And
Do people ever hash their own private key in order to create another private key? Like the hash of their private key is
It depends on which hash. That's probably not a good idea because, especially if you're using like ECDSA, because if you hash that and use that as a private key, this public key would be this private key, right? And does that make sense? So you're saying if I hash this private key and turn it into this public, and then I use this public key as my private key, like you could go ahead and hash it, but once again, that's not something you really want to do because if someone finds out your master key, and if they know what hash you use, it's very easy for them to figure out anything else. But one of the really cool things about this entire process is that any child private key can also be used as a parent private key. So basically, you can create not just child keys, but you can create like grandchild keys and great-grandchild keys. And one of the and each parent private key can actually generate multiple child keys. So one of the cool benefits that you get from this is you create something called a hierarchical structure, where basically, let's say one of the benefits of this is, let's say you have like an organization, a company, and you're the CEO and you want to control the master private key that basically created all the child private keys. Then you can give one private key to each department. So you want to give this private key to marketing, and basically the marketing will go ahead and create new private keys for all of its employees, so that way they can spend money. But you want the marketing person to be able, the CMO, to be able to access all the accounts for anyone under them, but not be able to access any siblings' private keys. So this allows you to create a really cool hierarchical structure that's very useful for example, organizations and companies, and a lot of other schemes you can put together using this method. And now onto a little bit of security. One of the big questions when choosing what kind of wallet to use is who controls your keys. The example, like I mentioned with Coinbase, is that they control your private keys. And the benefit of this is that if you ever forget your private key, you can go ahead and call them, say like, hey, what's my private key? But then the other side is you never know what they're actually doing with your money, because since they control the private keys, they could be spending whatever they want with it. That's why in the homework I asked like, hey, why are there weird transactions being done with Alex's money even though she hasn't spent it yet? It's because Coinbase controls her private key, so they can just do whatever they want with the money, just throw it around, and they don't really have to return it to her until she really asks for it. So in this sense, Coinbase is essentially just acting like a bank, pretty much. But on the other hand, like I said, you have stuff like Mycelium, which is you alone hold the private keys, so no one's doing any funny business with your money. But at the same time, if you lose your private key, you're shit out of luck. Like there's no one to call. There's no forgot my password. You are the sole owner of your key. So that comes with a lot of benefits and cons that you have to weigh. And then you have things like Case Wallet or green addresses, which allow like double authentication. For example, in Case, what you'll do is your device signs a transaction. The Case service also signs a transaction. So that way you have to get a 2 of 2 multi-sig, but you're basically, and they have a separate backup company that also holds one of the private keys. So it's 2 of 3. So the good thing is if you ever lose your device, what you can do is call Case, say, hey, I lost my private key, and you can call the separate backup company and say, hey, I lost my private key. Can you two put together your private keys in order to send all my money to a new account that I'll create? So it's a good way of using multi-signature, you can get a lot of these cool features such as like authentication, like security in case you forget your private key. Yeah. And so these are like some of the things you should consider when choosing a wallet. If you go to bitcoin.org, they have a great page that has a lot of information on a lot of the most popular wallets, at least. I personally recommend, I really like Copay and Mycelium. So that's my advice. And yeah, and so I talked a little bit about wallets and what they are, why they're used. Philip will now go into more about how they work.
All right, so I'm going to cover some basic cryptography concepts that'll be really helpful in understanding not just how Bitcoin works, but how other protocols built on top of Bitcoin work. So we're going to start by covering cryptographic hash functions. These are really important. When Sunny mentioned SHA-256, that's an example of a cryptographic hash function. And there's several key properties that we want a cryptographic hash function to have. So basically, a cryptographic hash function is a function that evaluates in one direction. In other words, it kind of takes some data, sends it through this one-way pipe, and gives you some garbage. Except you can't go backwards through the pipe and get the data back again. It's like making a stew. You put the eggs, the potatoes, the carrots, the soup. You mix it together, but you can't get the parts back out again. It's also deterministic, so the same input always yields the same output. And you can see this notation. We define a cryptographic hash function h as a mapping from some arbitrary length bit string to a k-size bit string, essentially. So SHA-256 maps some arbitrary data to a 256-bit output string. There's also a key effect, or a key property called the Avalanche Effect. And what this means is that if you change a single bit in the input, there will be a huge change in the output. So to give an example, if I do a SHA-256 digest of a bunch of A's, I get this hex number. If I do a SHA-256 digest of a bunch of A's, except I change the last one to be a B, it's a totally different number. If you just eyeball it, the numbers are completely different. And this is really important because you don't want numbers that are near to each other or data that's close to each other to have similar hash values. You want them to be totally uniformly random over the output space. And if we go now into some more formal properties, the first one we're going to talk about is preimage resistance. And this is kind of alluding to the one-way property. Essentially, in intuitive terms, it should be really hard, extremely difficult to go from an output of a hash function to the preimage or the input. And when I say extremely difficult, it's kind of hand wavy, but essentially it means it should be computationally difficult. And there are stronger security proofs that you can read into if you want to know more about that. In our kind of hash notation, we essentially say if you have some public output y from some hidden input x, it should be pretty much impossible to find some sort of inverse function that maps back to x. So that's preimage resistance. Okay, there we go. The second property, which is very similar but subtly different, is called second preimage resistance. And this is essentially if you have some specific input, finding any value, if you have some specific output, finding any other input value that maps that same output should be also difficult. And this is subtly different from the first preimage resistance, but it's a stronger security property, I suppose. And then finally, there's collision resistance. Essentially, this is saying that it should be impossible to find any two inputs that map to the same output. So if you see in our notation, there are kind of two ways of framing this. The first is that if you have two messages, or two inputs, x1 and x2, the probability that their hashes are the same should be very small. And it should also be uniformly small across all of the input pairs. Or kind of equivalently, finding any two inputs that map to the same hash output should be computationally difficult. And just guys, kind of like an interesting side note, the upper bound in terms of computational complexity to find any collision in a general hash function is 2 to the n over 2, where n is the number of bits in the output. So for SHA-256, it has like 2 to the 128, essentially, computational complexity in terms of the number of hash attempts you have to try. And this is called a birthday attack. And it's kind of similar to the I'm sure some of you have heard this in like CS70, but like if you have more than 35 people in a room, the probability that any two people have the same birthday is like above 99% or something. And this is kind of a similar property. Yeah.
So the whole determining whether you can have a unique public key depends on whether the private keys are unique, because the hash function everyone uses is the same. And you said you randomly generate the private keys locally.
Yeah.
Who's to say that there isn't another private key that already exists that's the exact same one as you randomly generated? And in that case, it'd be a conflicting public key.
Yeah, that's a very good point you bring up. The reason why we kind of assume that there can't be conflicting private keys is because the private key space, in this case, they are 256-bit elliptic curve digital signature keys. 256 bits is a lot of space. You have a 0 or a 1 for each bit, and you have 256 of them, so you have 2 to the 256 possible permutations. And to kind of give like an intuitive understanding of how large that is, that's like more than the number of atoms in the universe. That said, I mean, if some people use the same like input entropy to generate their keys, then they might have the same like key, which would be bad. We just generally assume that people have enough entropy in their random generation to generate different keys. And that's a key security step, is that you want to have enough randomness to generate good keys. Otherwise, someone might find it.
What happens if it's
If there's two, well then technically both of you own that key. And if someone else like owns that key, you can spend from it. Which is why like there are attacks that attack on the pseudo-random number generators that actually generate the keys. But yeah, it's a good point you bring up. So you might be wondering like why these hash functions are useful. Max last time talked about Merkle trees, and hash functions are really important in Merkle trees because they let you essentially prove the existence of some hash value in the Merkle tree with like a logarithmic number of data points, essentially. I think we're going to be covering Merkle trees again, I think next lecture, and it should kind of make more sense once you understand how hash functions work. Additionally, there's proof of work where we kind of use the evaluation of hash functions as a way of proving that you've done so much like work, where one evaluation of a hash function is equivalent to like 1 unit of work. And the important thing is you can't like take the desired result and go like backwards to the hash function and get the desired input, because otherwise the proof of work wouldn't work, because you could just like generate the input that gives the output. And also in Bitcoin, all the transactions, blocks, and addresses are all referenced by hash value. It's kind of a low-level implementation detail, but there's also several other additional useful applications in HMACs, which are like hash-based message authentication codes, password verification for like, I don't know, Google like database or something, commitment schemes, which we'll cover in a second, and pseudorandom number generators, which can be done with a like string of hash evaluations and a nonce. So to kind of illustrate these like formal properties of a hash function, we're going to look at a toy example that I call the simple hash commitment scheme. To kind of set up, let's assume that we have Alice and Bob, and they're going to bet $100 on the outcome of a coin flip. In the case where Alice and Bob are next to each other, Alice says, okay, I'm going to guess it's going to be heads. They bet $100. Bob flips the coin, and they can agree on who won. Now, in the case of like these sort of distributed systems, Alice and Bob are separated by a network, and additionally, they don't trust each other. So it's kind of easy to see a way that Bob could cheat Alice. Alice guesses the outcome of the coin flip, sends a message to Bob. Bob sees Alice's guess and goes like, oh, she guessed heads. I'm just going to say it's tails, and sends that back to her. And she can't know either way, and immediately loses her $100. So we're going to develop a simple protocol to fix that, essentially. So this is kind of a wall of text, but essentially, we're going to say Alice chooses a large random number, R. She guesses the outcome of her coin flip, B, which will encode as a 0 or 1. She'll generate what's called a commitment, which is the hash of the bit guess concatenated with the R random number. We'll call this C. She sends this commitment to Bob. Now, Bob can't see what her guess was because it's been blinded by this hash function, essentially. He can't go backwards through the hash function and find her original guess. So Bob has no choice but to just flip the coin and send the result back to Alice. Then Alice essentially unpackages her commitment by revealing her random number and her guess. And so then Bob gets these revealed numbers and essentially just checks that the revealed number and the revealed bit map back to the same commitment. And if they do, then he knows that Alice didn't cheat. And in that way, they can both trustlessly agree on who won the hash game or the coin flip game. So if we look at how they might cheat, how could Bob cheat Alice? Well, if Bob receives the commitment and he can somehow go backwards to the hash function and see what Alice's original guess was, he could just send her the opposite guess. But because our hash function is presumably preimage resistance, this shouldn't be computationally feasible. In the other case, how could Alice cheat Bob? Well, if she can generate a commitment and then see Bob's flip result and then generate another commitment with the opposite guess, but that maps to the same commitment, then she could send those back, and Bob can't tell the difference. And he's like, oh, this is fine. However, if our hash function is second preimage resistant, this shouldn't be possible. So that should be like a kind of a simplish explanation of why preimage resistance and second preimage resistance are important in some of these cryptographic hash functions. So briefly, I'm going to talk about elliptic curves. Basically, all you need to know is that we kind of formulate an analogy to multiplication over this elliptic curve using points on the curve. If you've taken Math 113, it's like a finite abelian group. I won't actually go into too much detail about this, but this is the elliptic curve that Bitcoin uses, SecP 256K1. Yeah?
What is the reason for using it?
Without going into too much detail, essentially the reason why we use elliptic curve cryptography is because it gives us much smaller key sizes as opposed to RSA if you've taken CS70. I actually have a slide. I'm going to skip all the math, but it's there if you want to look at it. Essentially, we can formulate a discrete logarithm problem on top of these elliptic curves. Again, I'm going to hand wave over this because it's not super important. But the reason why we use elliptic curves is because they give us much smaller key sizes. So for equivalent security to a 128 bit block cipher, we need a 256-bit elliptic curve key versus a 2048-bit RSA key. So it's a lot more space efficient, and it lets us do public key cryptography. And that brings me into digital signatures. So digital signatures are kind of analogous to a handwritten signature. So if you want to cash in a check, you got to write your signature on the back, and that way the bank can tell oh, this person obviously validated this check, and we can send it through. A digital signature kind of works in the same way. You have some sort of message, and you want to like generate a signature that basically proves that you were the one who sent that message. It should be really hard to forge a signature, like your signature, without actually owning your private keys. And you can see this in this example. I can sign the text "Hello World" with my GPG private key. So there are a few, yeah.
So the big picture on the signatures, I know it was in the initial readings.
Yeah.
When a Bitcoin transaction happens, you sign it, and then other people verify your signature, and they consent.
Yeah. So in the context of Bitcoin, you own private keys to the outputs of a transaction. In order to spend those outputs, you have to basically prove to other people that you own those outputs, and you prove that using a digital signature scheme. So essentially, you generate a signature using your private key and the output hash, basically, and you generate a signature. And using your public key and your signature, other people can verify that that was in fact a correct signature, and that you own that private key. Except the cool thing is they can't tell anything about that private key. All they had to use was your public key and your signature. Yeah?
How exactly do they verify based off of just the public key and signature? Is it not making
well, there's I have the math written here if you want to look into it. It relies on the group law for elliptic curves. You just have to know that it's mathematically possible for this to happen. I won't actually go into the proof. I don't know. It's too dry for this. But all you really have to know is that for a digital signature scheme, you basically have 3 properties that you want. First is message integrity. So between me signing the message and someone trying to verify the message, someone shouldn't be able to change the message and have it still validate correctly. For message origin, you should be able to tell that if the signature and the message validates, then in fact the person with that private key must have been the signature signer. And non-repudiation, so if someone signs a message, they can't backtrack and somehow say, oh, that wasn't me. And so how we kind of distill that, we distill that into 2 algorithms. We have the sign algorithm, which takes a message and a secret key. And so using the message and the secret key, you generate a signature. And that signature is what you distribute to people in order to prove that you signed that message. Then you have the verify algorithm, which takes the signature and the public key and outputs a 0 or a 1 if it's in fact a correct signature. And for Bitcoin specifically, they use elliptic curve, the elliptic curve digital signature algorithm for signing transaction outputs. Again, you don't really need to know much about elliptic curves or even the algorithm itself, other than that it just provides a signature algorithm. And I left the proof sketches in the slides if you want to check that out, but we don't really have time, so we're gonna skip that. Yeah, and so basically, ECDSA, the elliptic curve digital signature algorithm, is used to prove ownership of the transaction outputs in a Bitcoin transaction, and that's how you can provably spend money.